So then now the next slide is about the names for the packets. What do you call a packet? Every layer has a different packet, and it's better to call them differently, and therefore ISO, the original standards which back in 1984, which actually never got caught on too much rest of the layers, but this nomenclature actually is used even in right now. So the thing is, every layer has two things, SDU and PDU, service data unit and protocol data unit. SDU is what comes through the door, and PDU is what gets out of the door. So if this is a layer, then SDU comes in and PDU gets out. SDU is service data unit, what comes in. Generally, that becomes the data for that layer. A header is added, and that becomes the PDU. And it may not become a PDU because in some cases, it may be broken into something and then put a header, so all that is done. So whatever goes out, basically PDU goes horizontally. So if I were to draw this, and I don't have that picture here, you draw two layers, the receiver and the transmitter. So the data link of the transmitter sends something to the data link of the receiver. That would be the data link layer PDU. The network layer of the transmitter sent something to the network layer of the receiver. That would be the network layer PDU. So whatever goes horizontally is PDU. Whatever goes vertically is SDU. And the SDUs kind of keep changing from layer to layer. So basically, whatever comes in here to LLC would be LLC as SDU. Then it sends it down to MAC layer, that will become MAC SDU. And then it sends it down, that will become that SDU. So every layer has input and output. Right? So the output of one layer becomes the input of the other layer. All right? So when I say from now on, MSDU, that means MAC SDU. And whatever will come out of MAC will be called MAC PDU, MPDU. And that will become physical layer convergence procedure, that is the next layer down, PLCP SDU. Right? And this will produce a PPDU, which will go to the PMD, and so on and so forth. Now, PMD does not have SDU PDU because PMD just so happens is the physical media dependent layer, which are just the bits going around. There may not be frames. So frames are up to here, right? So we will be using these words: MSDU, MPDU, PSDU, PPDU, and I can take it up to the network layer. They would be called NSDU and NPDU. Now, in the TCP/IP world, this terminology was not used, and so they didn't really have such clarification. But NPDU is what we call datagram, right? And packet. No, the packet actually doesn't say which layer it belongs to. So the packet is very confusing. But if you say datagram, then in the TCP/IP world, datagram means IP packet. Okay? TCP packet is called segment. So PDU would be segment. And application PDU, I think it's called packet or something, or message. Application PDU is called message. So messages become segments, segments become datagrams, datagram becomes frame. So yes, the Ethernet things are called frames, and those would be MAC PDU. So they use these different words, but in the ISO world, they had a very standard thing. You can even call them L2 PDU, L3 PDU, L4 PDU, L5 PDU, and so on and so forth, L3 SDU. So you can call it by layer number, or you can call it by layer name. Okay. Now, the physical layer is divided into two parts, as you see in this picture. One is the physical layer convergence procedure, PLCP, And then second one is PMD. PMD is pure physical layer, pure bit by bit thing. It doesn't really know much about the frames. The thing that knows about the frame in the physical layer is this PLCP. Okay, so if we have to do anything related to frames, that will be done in PLCP in the physical layer. Now, physical layer doesn't know about the access method and things like that. All those are in the MAC layer. MAC layer is the one that we were talking about as to when to transmit this and that. Physical layer, once you transmit it, will just send it, using whatever QAM, this and that stuff, right? So physical layer is different from the MAC layer, and the logical link control, actually, again, all of this is 473, but I'm just saying it here because a lot of people don't teach all this because they were never exposed to ISO. And I was exposed to ISO up to here because in the days when there was a debate between TCP/IP and ISO, I was in the ISO camp. I was working for digital equipment, and digital equipment wanted ISO. And actually, all the companies wanted ISO. The academic community came up with TCP/IP, and the government gave it free to everybody, so everybody just switched. And then, we switched. But so ISO didn't happen, but we wrote a lot of it. We used a lot of it, and there are a lot of things related to ISO in DECnet and so on and so forth. This is all back 1984 and before. So anyway, so this is still used though, this SDU stuff. So I want to make sure that when I teach 473, I cover these things because we need this. Any question about PDU and SDU? By the way, LLC and MAC, I don't know how many professors teach LLC, but again, LLC is, so on the network, you have not just one wire, you have bridges between the wires, right? So you have Ethernet, actually we call it Ethernet segment, another Ethernet segment, 2 wires, then there is a bridge, and so on and so forth. So if you go from here to there, that is the whole Ethernet, not just, one segment. So when you cross the bridge, then you need LLC, logical link control. Okay, so logical link control handled all the bridging stuff, and the MAC was basically how do you access the wire, media access control. And there were different kinds of LLCs. They're all history now. Ethernet had a different LLC than token ring. Token ring is no longer there. Again, tokening is no longer there, but lots of academic people still teach it because they're not aware that it is no longer there. It died in 1999, so 16 years ago. So the idea is that there are things which are alive, things which are dead. So right now, basically LLC, I use the word LLC, so I just want to make sure that, at least that this is, we won't be talking LLC at all in this course, but there is this layer. We will start with MAC. We will have MSDU, MPDU, PSDU, and PPDU. Yeah.
Is the PLCP part of the actual wire itself, or is it some interface between them?
So what happens is when you give a packet, when you give a PSDU to the physical layer, it adds some bits in the front. Why does it add some bits in the front? So that you can figure out that a packet is coming. See, by the time you figure out the packet is coming, some bits are gone. Right? Not only that, you may be on the wrong timing. You think the bit starts here and the bit starts there, so you need some synchronization. So they add some synchronization bits in the front. Right? They tell basically that, look, I'm speeding at this speed, and now a packet is going to come. So you synchronize to that, and then by the time the first real bit comes in, you are all ready. That is PLCP. All right, so let us see. So actually there's more to it. What I said was just the prefix. So what we do is we take whatever bits are coming in from the MAC, those are scrambled. Scramble means randomized. Okay, you might send 000 and it might become 01110. I mean, basically there is a shift register, like random number generator. Shift register, you shift the bits in and they come out differently. Okay, randomized. So that is called a scrambler. Once you scramble, then you do the block coding. That means you take many different bits, like 4 bits from here, 4 bits from here, 4 bits from there. These are different blocks. And then you interleave the blocks. So you see there is a black block and there is a red block, and the bits come out like this. They're interleaved. Then they are converted into symbols. Now these are bits. We want to get, let's say you are using 2 bits per symbol, then they will become 00, 10, 11, 01, 1011, right? And then we do the modulation. Let's say we are using 4 QAM, then we decide the amplitude and modulation. Yeah.
So at the receiver part, the receiver knows how the scramble.
Yeah, right. So everything is standard. Anything that is random has to be standard, otherwise it would be confused totally, right? So everything here, in fact, the block coding, interleaver, modulator, everything is standard. And so the receiver knows that this is a 4 QAM. The receiver knows that this is, everything else. If you change anything on this side, the receiver will know on the other side that this has changed. And they will just follow the opposite direction exactly same way to get the same bits.
So when do you use this?
Okay, yes, that's coming up. Okay. So basically, that is coming up in a minute, right? So basically, what comes out of here, then you put something else in front of it. You put some sync bits, which are 80 bits of sync. 80 bits of sync. Those are shown here. This is not always the case. 0101, 0101. You just send 0101, 0101, 80 bits. Why 80 bits? Yeah, because that's how long it takes for your circuit to wake up. It was sleeping, remember? You wake up in the morning and suddenly you get the message. You say, what? Right? So that's what for 80 bits it takes. Then there is a start of frame delimiter. Then there is a special bit pattern, which is this in this case, 18 bits. And when you see instead of 0101, you see this, then you know now a frame is beginning. Now I got to figure out somewhere where the address is, right? Yeah. Yeah, I think this could be 16-bit. I think this is just a typo. Because 18 doesn't make sense. Okay? And so 16 bits of this SFD, then 12 bits of length, 4 bits of data rate, 16 bits of HEC, header error check. This is a CRC just for the header. Okay? And then the header, whatever, right? And so this is all part of PLCP. So PLCP knows the header, knows the frame, knows things. PMD doesn't. You see, this part doesn't know anything about the frame bits or anything like that. All right. Now, so the question was asked, actually, you asked the question as to why we have to do all this scrambling. This is because so that we can make the errors distributed. You see, if I am sending 2000 bits. If my middle 100 bits are lost, it's very difficult to correct it. But if my first bit, 100 first bit, 200 first bit, 300 first bit are lost, I can easily correct because of my CRC and because of my thing, right? So we want the errors to be distributed. The noise is not. Noise you have no control. Noise is bursty. Noise will happen whenever it happens. And so by this method, as you can see, what happens is the noise goes all over. So if I get this 2 bits gone, I'm sure that one is from this block and one is from that block. Right? And then those bits, even if there were, let's say, 4 bits here, then there are 2 from this block and 2 from this block. Those 2 will not be just next to each other. They would be from some places somewhere else. Right? So I have better chance of correcting them. So all this randomization, all it does is takes this thing which happens at a very instant of time and distributes it over multiple instances of time, because then bits are all from all over come here. You see what I mean? Yeah.
red bits are constant for every output of block coder.
What is constant?
The red bits, I mean.
No.
Depends on the output of the block.
No. Yeah, right. There might be many blocks. Okay, so just imagine that there are many block coders and many scramblers. So it is just, I mean, I haven't shown it, but red is another chain which is coming in. The multiple blocks. Actually, another way you can do it, okay, block coder puts its 5 bits here, the next 5 bits here, and then 5 bits here. So all these blocks are here. Now you merge them. If you have just one block coder, then you can just store them and merge them later. If you have multiple block coders, they could just be coming in and going out. So here are blocks, and the blocks could be 8-bit, 16-bit. As shown here, it is 6-bit, which is kind of not reasonable, but good enough for this example. So bits, blocks, frames, right? And so this is blocks. So everybody understands what is PLCP, what does PLCP does, and then what does PMD do? PMD is the top, PLCP is the bottom. All right, so now that we understand PMD and PLCP and PSDUs and things like that, so let's go to 802.11b, which was DSSS, Direct Sequence Spread Spectrum, Complementary Code Keying. Okay, and so this is called bits, which are what you are wanting to send. What goes on the medium is called chips. We already introduced that notation, right? Because each bit becomes a number of bits. In this case, in case of 802.11b, 11 chips per symbol. Each symbol is just 1 bit long. All right? Each bit becomes 11 chips. And then we use differential QPSK. So QPSK gives you 2 bits, right, per hertz. So you get about 2 megabits using 22 megahertz. How do you get 2 megabits? Because 22 megahertz, you get about 2 chips per hertz. 2 chips per hertz. Right? So that gives you 11 mega chips per second. And then you divide that by 22 becomes 44, 44. And then divide by 11, by whatever. Basically, so you should get 2 megabits per second. Let's just do that correctly. So you will get 2 megabits per second using 22 megahertz. Okay, so let's just do this one more time. 22 megahertz gives you 44 mega chips divided by 11 should give you 4 megabits per second. I'm missing somewhere a factor of 2. QPSK. Oh, okay, sorry. It is differential QPSK. It's not QAM. Phase shifting, quadrature phase shift. I think you can only get 1 bit per hertz. Okay, QAM gives you 2 bits per hertz. QPSK gives you 1. So that is what they want. So 1 times 22 divided by 11 gives you 2. 2 megabits per second. Okay, and that was in the original 11. In the 11B, they used 8 bits per symbol and 8 chips per symbol. Okay, so now instead of 1 bit like this, they will take 8 bits and then translate into some other 8 bits using some code. Okay, so each symbol has 8 input bits as well as 8 output chips. So now you get basically, now you do the multiplication. 22 megahertz becomes 22 mega chips divided by 8 multiplied by 8 you get 22 megabits. Again, I'm missing a factor of 2. I'm missing a factor of 2. So you got 11 at the end, and now I got to figure out where the 11 factor of 2 is. But basically, using these numbers, you should be able to figure out, given how many bits per hertz you get, you should figure out that how many hertz you have, how many bits you will get. At the end, you will get 11 megabits. Okay, I will figure out that factor of 2. Okay, all right. 11A went on to better modulation, and it from BPSK, QPSK. Actually, here are the numbers. I am probably off by factor of 4. It says QPSK is 2 bits per hertz. So anyway, so basically OFDM. So 11A introduced OFDM, 64 subcarriers in 20 megahertz. 6 subcarriers at each end are used as guards. So basically 4 as pilots. So these are the guards. These are pilots in the middle. So you have about 48 for data. And so instead of 20 megahertz, you really have 12 megahertz for data, because out of 64, you have only 48, which is 3/4. So instead of 20, you have 3/4 of that. 3/4 of that would be 15. We have 60%. Anyway, so out of these, basically we get 12 megahertz for data. And using BPSK, you get 1 bits per hertz. That will give you 12 megabits per second. If you do half FEC, forward error correction, that means for every bit you send 2 bits. You will get 6 megabits per second net. On the other hand, if you send using 3/4, where for every 3 bit you send 4 bits, you will get 3/4 of this, which is 9 megabits. If you do half, and so on and so forth. Okay. So one thing is that by multiplying these numbers, you should be able to get megabits per second. And you should be able to figure out how many bits per hertz there are, right? And then since the hertz is given, you can calculate the megabits, and then the coding. Coding is these fractional codings. Basically, all you do is multiply, and you get the rate. So 1/2 means 1 bit data, 2 bits sent. 3/4 means 3 bits data, 4 bits sent. So you add 1 extra, right? 2/3 means same thing, 2 bits data, 1 bit extra. Yeah.
So in the previous slide, that would be a 1 to 10 ratio?
1 to 10 ratio. Which one, 11 or 11B?
Look at in that picture there. You have 10 bits of signal.
11 bits actually.
Is that 11?
Supposed to be 11. 0, 1, 2, 3, 4, 4, 8, 2, 10. I have shown 10, but they're supposed to be 11.
Oh, okay. It's supposed to be a 1 to 11. That's the ratio?
That is 11 chips per symbol. In the original 11, we had 11 chips per symbol. Now, this is not the ratio. Okay, let's don't confuse. Okay, hold on. So, let's just start with the bits alone right here. Okay? In fact, maybe even before this one. Right after the modulator, I have not shown it to you here. Whatever comes out, either before the modulator or just after the modulator, I'm not really sure at this point. We will add extra bits. That's the bits I'm talking about. FEC, error correction.
I think before the modulation.
Before the modulation. Yeah, before the modulation, we will add extra bits. Yeah. Okay. So, so the error coding, actually, I have to figure out where the error coding is. It could be, in fact, it could be even here, beginning. It could be anywhere.
Yeah.
Huh?
Yes.
It could be anywhere. But I think they have a particular place where they do it, and looks to me that the best place would be right in the beginning, right here. So somewhere they increase the number of bits. So instead of 2 bits, you have 3 bits. 2/3.
What does the error correction do? Is it just to like kind of water down the chance of an actual data bit getting...
Oh, error correction. So actually, I mean, again, okay, this is something 473. In 473, we teach about error correction, but I'm going to just give you an idea. So if I send an extra bit, then we can figure out whether the bits are wrong or not, right? But just parity bit. This is how the parity works, right? If the parity doesn't match, then we know that this is wrong. Right? Odd and even parity. And if you add 2 parity bits, then it can tell you more than that this is wrong. It could tell you that the second bit is wrong, and you can flip it and everything will be okay. That would be error correction. Right? So, but this is not, parity is not the end of, this is the beginning of the error correction. There's a whole course that can be done on coding theory where they teach you how to get the best error correction with the minimum number of bits added. So here, there is more than this actually. It doesn't really show you. I mean, this is actually, see what this picture, even though it shows FEC, there is one more coding which is done, which is not shown here, Reed-Solomon coding, which will come up in the next lecture that we have, number 7, where we have multiple levels of these error corrections also. Okay, but for this picture as shown, you can calculate these numbers using these things. And actually, user never sees any of this number, by the way, because the user gets much less than this. Most of this is header and CRC and this and that, and RTS and CTS. By the time you bring down to the user sent, it will be 1/4 of it. Right? But at the physical layer, this is the bits you can get. By the time you come to the user layer, there is a lot of headers and things like that. Okay. So anyway, so few things from this slide, please. One is that you understand guard, and you understand pilot. This is for OFDM. In OFDM, we have many subcarriers. Some are used as pilots, some are used for data. And towards the end, you don't use them because everything is going to overflow. Even the middle ones are going to overflow, but the end ones will overflow into somebody else's domain, and that is considered bad, and that is regulated. So the end ones are generally used as guard. Okay? So that's what it is that after, yeah, that's all it is shown here, and those are the words, right? And then, okay, that's all. And basically this 11A was 5.4 gigahertz. It didn't become popular because it was just 5.4 gigahertz. Actually, 5.8 is the right word, but people use 5 gigahertz, 5.4 gigahertz, 5.8 gigahertz. We saw that band. Different naming. Then G came about, and G did the same thing with the same thing except in 2.4 gigahertz, and then it became very popular. And the advantage of 2.4 gigahertz was that now you can go back to the old devices and talk to them CCK, the complementary code keying, whatever that is, right? So B and G are more compatible than B and A. A will have to switch the band. B will not have to switch the band. Now, before we go to the next level, then comes E. And E is not a new wireless standard, it's a new QoS standard, quality of service standard, 11E. And so they said that, well, wireless is good, but we cannot talk over the wireless because everybody gets the same service. The voice should get some priority service and things like that. So we introduced some priorities and different levels of different priorities and so on and so forth. So that's what 11E does. And so they introduced, instead of DCF, they changed to HCF, hybrid coordination function with two components, contention-free hybrid polling and contention-based enhanced DCF. And the DCF was changed. And I will explain a little bit as to how it was changed. DCF is that diagram that we just finished with the hatch area, right? That is the DCF, distributed coordination function. And then they added direct link, where the station traffic can be sent directly between the two stations. They added frame bursting, and the frame bursting means that you don't have to send just one frame. Once you get this RTS CTS, you can send more frames, 5 frames. So in RTS, you say, well, I want to send 5 frames. And if you get CTS, you can send 5 frames. Okay? So frame bursting and group acknowledge. Obviously, if you're going to send 5 frames, you want one acknowledgement saying that I got all 5, I got 4 or whatever. So that is group acknowledge. Multiple priority levels and automatic power save delivery. And so automatic was where you didn't have to request. Basically, previously when you woke up, you told this guy that, okay, I'm awake, please send me my frames. Now, this new mode was added where, you tell them, oh, I'm going to wake up every morning 6 o'clock. That's it. So 6 o'clock, your packet will be delivered. Automatic. One packet is saved. Basically, you don't have to say request. You get the packet delivered. All right. So previously, there was a beacon. After the beacon, there is a contention-free period, which is called point coordination function. Then there was a contention period, which we call DCF, distribution coordination function. If you remember from the previous module, right? Now it is much more complicated. After beacon, there is HCF, hybrid coordination function, which is contention free. Then there is enhanced DCF, which is contention period. But contention period is in 3 parts: enhanced DCF, HCF, and enhanced DCF again. So basically, so there are 2 kinds of SCF here: contention based and contention free. So so basically, they allowed 4 priorities, and each is kept in a separate queue. So the packet comes in, then we decide what priority it goes in. It's like having 4 stations in the same station, inside the same station. And each priority had a different value for CW min, which is the contention window minimum, contention window maximum, IFS, which was the interframe spacing, transmission opportunity, and BO backoff. Okay, so some of these are parameters, some of them are variables. For example, backoff is a variable which is random number between CW min and CW max. So the higher priority will draw a smaller number, and the lower priority will draw a bigger number. Yeah.
How comes the CW max is basically
CW what?
For the first priority, the maximum backup that comes is basically 1. Right?
CW min upon CW max. Are you on this line?
No, I mean for the first priority.
For the first priority, yeah.
The maximum is 1, right?
Maximum is 1. No. This a square bracket simply means array index. So you have CW min is an array of 4. So this is the first value, the second value, third value, and fourth value. This is just an array. Sorry, it is not the value. Similarly, everything is now an array. AIFS is an array, TXAP is an array, BO is an array. Any other question? So now you can see how the priority will be done, because if you have stations which are consistently drawing a smaller number, they will get higher priority than the stations which are consistently drawing higher numbers. So basically, you arrange all these parameters so that the lower priority gets better advantage. They get first. Only when they are done, the other priorities get in. Now, frame bursting is that Okay, so remember, okay, actually I didn't explain AIFS. So this is, you remember we had SIFs, short interframe spacing, and we had PIFs, point coordination, and DIFs, distributed coordination function spacing. So now we have AIFS, axis interframe spacing. A means aggregated or axis, whatever, right? So that one for these, so this could be changed so that this is smaller, this is larger, this is larger, this is larger. So these guys will have to wait for a long period before they can even draw their random number, because if the medium goes busy before that, then they say, okay, I'll write next time. If the medium is empty for that much period, then only you draw the random number, right? So these guys will get in faster, simply because AIFS is smaller. Okay, so you will send the data, wait for the acknowledgement data, get the acknowledgement data, get the acknowledgement. So this is a burst. Okay. Now this doesn't do group acknowledgement yet. That will be next one. So right now for each packet there is an acknowledgement right after the packet, but you don't lose the medium. You can continue to keep the medium with you because you have reserved that in RTS. So EDCF parameters announced by the access point in the beacon frame cannot overbook higher priorities. So the thing is that all the higher priorities have to be booked, have to be reserved. So you can say, well, I want to do 3 megabits per second, and the station will give it to you. If you say I want 55 out of 55, they will say no. I mean, obviously, I think there's no guideline in the standard which says you have to, when you have to say no, but just the practice is that you don't want to reserve more than 25%, and everything else has to be left in the contention period. Okay, so EDCF allows multiple frame transmission, maximum time. So the maximum time that you can transmit this whole thing is called transmission opportunity, TX-op. So that is a parameter that is limited. So that is announced. So if we go back to this one, you see there is a TX-op 1, TX-op 2, TX-op 3. Previously, TX-op was equal to the maximum frame size. Now it is multiple times the frame size. All right, so we have TX-op, and we have SIFs and PIFs and everything else as before. Instead of PIFs, now we have AIFS, which will be basically for whatever priority you have, that is the time you have to wait. Okay. All right, direct link is very easy to understand. You tell the access point that I need a direct link to this station, and then the access point will say go ahead, and then you can send it directly. So that way you don't have to have 2 frames for each frame. Automatic power save delivery, I have already talked about APSD, but first is unscheduled. Access point announces the waiting frames in the beacon. Unscheduled means that basically in every beacon there is a list of stations whose frames are waiting at the access point. So whenever you wake up, you listen to the next beacon, and if your frame is there, you send a request and you get it. That is unscheduled. Scheduled is, which is basically the station tells that I will get up at 6 a.m. and then you get your frames delivered at that time. Yeah.
So this new feature helps that bits that we use for synchronization.
Okay, no. The question was asked in the PLCP, there is 80 bits of that can be reduced. That has totally orthogonal to this. So I had just given a simple explanation that I'm just waking up from sleep and therefore I need some time to think. But even if you're not waking up asleep, you are doing something else, transmitting, going to receiving, from receiving to transmit. So there's a lot of turnaround time. So those 80 bits are required regardless, even if you don't go to sleep.
I know, makes sense.
Okay, I mean, I just gave an example, but there are many reasons that you don't want to just be able to get the first bit. Yeah.
Like the 80 bits sounds somewhat arbitrary. Like, is there a reason why?
Yeah. Okay. So it's not arbitrary. What they do is this cost versus performance trade-off. If they reduce it to 40, then they will find out that 10% of the frames were lost. I'm just making up a number here, okay? And so somebody must have done some measurements that today, given that I want a $5 device, not a $50 device, with $50 device I can do it. But for a $5 device, I really need to wait so many milliseconds, and that means I need this many bits.
But we lose the data rate.
Yeah, so the thing is cost performance trade-off, right? So the cheaper you make, the performance you lose, right? If you want higher performance, you go to the higher cost. Now, because we are designing a standard for the whole world, we cannot really design it for high cost too much. So we put our cost goals, as we call it, and somebody does, in the industry, somebody does, some simple implementation, and they say, yeah, this is very, very difficult to do. So all these numbers come from those experiments. Or, one of these professors, publishes a paper and says that, well, 60 seconds, we can do it in 60 microseconds or whatever, and then the number becomes the standard. Right? So it could come from anywhere. Yeah.
Is there conceivably a way to do that dynamically, like an access point census, like what's the worst of the devices connected to it, and then
okay, so here the thing, anything can be done, but the more rules you make, you are increasing the cost. Remember this, because now you are increasing the rule, you are increasing the complexity. If we could do dynamically, we could leave it to the manager. A lot of parameters are left to the manager. Okay, so when you buy a new access point, if you really go into advanced mode, it will ask you whether you want higher amplification, lower amplification, short gap. There are lots of parameters which we don't touch, right? But they're all there.
These are standards.
Yeah? No, the standard allows those possibilities. The thing is, there are several things, as I said. First of all, standard allows lots of possibilities. Industry cuts it down. And then the management cuts it down even further. Because industry cuts it down, and then if you are very smart, then you can probably play in that area, but most of us don't change any defaults. Right? So default is just one value, but there is a range that is allowed, even by the product. All right. So we know scheduled and unscheduled. This is we had already covered before. Now, one more difference is that there is no more bit required. So basically, before 11E, access point announced in the beacon, the station polls and AP sends one frame which says, I have more for you. And then the STA says, okay, I am ready for the second one, and then it sends the second frame. So there is this back and forth for multiple frames. And after 11.E, it could just burst it to you. All right, so you have 11.6, homework 6A, and this is fill in the blanks. I think you should be able to do this if you read the homework. If you read the handouts and the reading list. Make sure that you read the reading list. Now, here's the thing though, this homework is due when? And next Monday is what? Yeah? Exam. So I know that you will do it. So you don't have to submit it. If you don't do it, you lose. Right? So this homework is not due. Just because coincidentally it happened to be on the week before exam. Sometimes this same chapter we could have finished last Wednesday, then it will be really due. All right, so we move on to 11N. Any questions on 11E? Actually, when you read it, you will come up with more questions. Please do, and please ask the next time. 11N. So 11N introduced 4 new things. First is MIMO. And we already talked about MIMO. How many antennas you put and how many antennas you receive. And so given N by M colon K, where N is the transmitting antenna, M is the receiving antenna, then K are the streams. How many streams you send. Okay? And basically what happens is these are the streams inside the receiver. Inside you might have, see here it shows here it shows 3 antennas, but only 2 streams inside. Okay. Okay, the number of parallel radio chains inside, which is less than the number of antennas. There is no point in having more than the number of antennas. So these two antennas are combined in this case, and there are many ways to combine. We said take the best of them, take the average of them, take the minimum, whatever. I mean, there are many ways. So this is the thing. So you want to 2 by 2 colon 2, or 2 by 3 colon 2, or 4 by 4 colon 4. So diversity, more received antenna than the number of streams. That is diversity. Beam forming is focused in one particular direction. And MIMO power save, which means that you don't have to have all the antennas on all the time. So now previously the station could go to sleep. Now the station could be awake, but the antennas could go to sleep. Okay. So that is what 11N did. Keep going more, or actually not 4 is 13. And it does frame aggregation. So you can put multiple frames inside a frame. Now this is different than frame bursting. Frame bursting is basically at the physical layer. This is more like IP segmentation and the assembly stuff. You know, you can take multiple frames and put into one frame. So it looks like one frame. If you have very small frames, then you can put many of them into one frame. Frame aggregation. Lower FEC overhead. So instead of 5/6, they use 3/4. Now 3/4 and 5/6, what is the difference? 3/4 would be 9 by 12, and 5/6 is 10 by 12. Reduced guard interval. So there is guard. We saw the guard in the frequency domain, but there is also guard in the time domain. When we send something, we stop for some time. Okay, so that the frames don't run into each other. And so that is called guard interval. So 400 nanosecond instead of 800 nanosecond. Reduced interframe spacing, 2 microseconds. So by the time 11N came, which is 10 years after the technology started, now we are shaving off everywhere, trying to get every last bit we can get. And so reduced interframe spacing, 2 microseconds instead of 10 microseconds. Green field mode, which means that don't implement ABG. Everybody has to speak N. That is difficult to do. So there is a mode there, but I don't think anybody uses that. Yeah.
Is the guard interval between symbols?
Guard interval is between symbols. Yeah. Yeah, between symbols, yeah.
Excuse me, it's lower because for each 5 we have 1 extra, but before we had for every 3 bits we had 1 extra. So 5 to 6 is less than. I mean, it's
So I am doing calculation wrong, huh? 10 by 12.
Because no, because for each 5 bits we have only 1 extra, but before for each 3 bits we had 1 extra. So it's lower.
Oh, okay, the lower is better.
Yes.
9, okay, so 10 by 12 is better than 9 by 12.
Yeah.
Yeah, I was just thinking in the wrong direction. You're right. Thank you. Everybody got that idea? So the point is, 5 by, the higher fraction is better. Higher fraction. If I do 1 after 1, that is better in terms of performance, although error rate. So there are two performance: throughput performance and the error performance, right? So 5 by 6 is better because we don't have too much overhead, only 1 bit overhead. That is 20%. Every 5 bit we add 1 bit, right? There we had, for every 3 bits we added 1, right? So the 33% overhead, something like that. So 5 by 6 is better than 3 by 4. Good. Actually, so I was just comparing the fractions. The lower fractions is better. So 5 by 6, whatever. You understand. The lower number of extra bit is better for the throughput, not so good for the errors. All right, so let's see greenfield mode. Everybody understood greenfield mode? Next thing was dual band. So N works in both 2.4 and 5.8. Space-time block code. And when you get an 11N device, which, today if you buy, I think you are going to get minimum, lowest, cheapest thing is 11N. You will have both bands, and you can decide whether you want to use both or one, and which one. Okay. So for example, at my home, I have not started 5.6. I mean, I first started 5.6 and then I turned off. Basically, and I don't know why, but basically this is an arbitrary decision. You can have different networks on those two too. I mean, then it asks me what is the name of your 5.6 network and what is the name of your 2.4. You could give the same name, you could give different names, things like that. Dual band. Space-time block code, and this requires explanation, STBC. And I think there might be a slide right after this. Channel bonding. Channel bonding means that you don't have to use 20 megahertz. You can use 40 megahertz, 20 plus 20, two channels together, three channels together. And this is now continuous. So now by the time we get to AC and other things, we are not using 20 megahertz. We are using this big, this big, this big. More subcarriers. Now they used 42 plus 4 instead of 48 plus 4 with 20 megahertz. So they used 4 more. So now here is what they are doing. They are taking 4 less pilot or something, 4 more for data. So again, it is good for throughput, but bad for error correction. And so 108 plus 6 with 40 megahertz. So now if you have 4 streams, each with 64 QAM, with 5 by 6 FEC and 40 megahertz with 400 nanoseconds. Okay. Now you multiply each of these. So this one, 400 nanoseconds is not very easy to multiply, but 400 nanoseconds is 800 nanoseconds. You have to see what is the symbol time, and this will come out as a fraction. So you put that fraction here. Okay. And then multiply all these numbers. Instead of 64 QAM, you put how many bits per hertz. And you will see that now you can get 600 megabits per second instead of previous 55 or 54 or something. All right. Now guard interval. Question was guard interval. Guard interval is between the symbols. You have a data symbol, guard interval, data symbol, guard interval, data symbol, guard interval. So basically, guard interval should be 4 times the multi-path delay spread. This is a rule of thumb. So if you are in a small room, the delay cannot be that large. The delay spread cannot be that large, and therefore, you can have a smaller guard interval. You can go to your thing and say 400 nanosecond. On the other hand, you're in a big hall or in a big area, like, near the library outside. Then, there are lots of reflection points. The delay spread could be large. There you would not want to change to 400 nanosecond guard interval. All right. So initial 11.8 design assume 200 nanosecond delay spread and assume 800 nanosecond guard interval plus 3200 nanosecond. This is the number I am missing. So if you have 3200 nanosecond data and 800 nanosecond, you have 20% overhead, right? And most indoor environments are 50 to 75. So if both sides agree, means receiver and transmitter agree, then 800 can be used in 11N. And so 400 plus 3200 will give you 11% overhead as opposed to twice that much. Right? So the overhead would be, instead of 1.22, it will be 1.11. I mean, you can multiplier here. For 400 nanosecond, you get 11% less overhead, whatever. So that is how you calculate. Okay, so everybody understands guard interval, how it goes into the picture. Now I have to explain to you STBC. Space-time block code. Now here's the thing, this was invented in a university, right? So it was invented by 1998 by Wahid Tarokh. And I put the name because I met this guy. So Wahid Tarokh, I think he was at Harvard basically when he did this. But anyway, I don't know where he is now. But anyway, 1998 by Wahid Tarokh. Transmit multiple redundant copies from multiple antennas. So his idea was that if you have 2 antennas, then you don't send the same information on both antennas. You should send different things which are related but different. So let's say we have 2 antennas and I want to send 2 symbols, S1 and S2. 2 symbols. Symbols are some group of bits. Maybe 4 bits is a symbol. Okay. And each symbol, when you code it, it has this, remember the 45-degree angle and other angles? So it has this horizontal part and the vertical part. We call it real and imaginary. Right? So each symbol can be expressed as x plus iy. I is the imaginary component, y is the imaginary component here. So basically what he said was, and this is interesting, is that instead of s, you have s star, which is the complement of that s, which means x plus iy becomes x minus iy. Conjugate of S1. Conjugate of S. Conjugate of S is that you just take the angle and reflect in the other direction, right? So if you have S1, so what you do is in 2 times, first time you send S1 from here and S minus S2 star from here, from the second, from the antenna 1, you send S1 and the second antenna you send S2. The second time is slot. This is time and this is antenna, right? This is time and this is antenna. Then you send minus S2 star and S1 star. This is looking mathematical, but this is what those guys do. I mean, those who are in the coding, in the communication department, they do this kind of math, right? But it's not very difficult to understand, at least the concept. So now in 2 time slots, we send 2 symbols, not a big deal. Our rate has not gone up. If we had 1 antenna, I would have sent, S1 in the first slot, S2 in the second slot. But now you have made the code stronger. So what is happening is, this is a space, antenna is a space, and this is time, vertical axis is time. If you do this kind of coding, this is called space-time block code. Now when this guy receives this thing, it can fix several problems. It has received S1 and S2 and then minus S2 star and S1 star. It can do some mathematics and figure out what is wrong, what is right, where the errors are, where the corrections are. Okay, so we have made better use of the time and space by sending conjugates. Okay, space-time block code. So space-time block code, this is rate 1. Rate 1, this is called rate 1 because your output rate is same as your input rate. Basically, you are sending 1 symbol per slot, right? But there are other codings which are less and more. So there are many space. This was the beginning of the space-time block code.